Okay, let's go ahead and work part C of this problem of the car going around a curve. And so we have a car going around a circular curve, and we're told that there's some fuzzy dice hanging from the rearview window, and we want to figure out at what angle they swing out from the dead vertical direction. So we know what's going to happen when a car goes around a curve like this. So if we're looking from behind at the fuzzy dice, in other words, you're in the driver's seat looking at the fuzzy dice, we know what happens when a car goes around a curve like this. It swings out into the curve. Okay? So it's going to swing out to the left. And so here's the situation. Again, this is best solved as a Newton's law type problem. So let's go ahead and identify the forces that are acting on the dice here. Okay? Now, of course, gravity is always at play here. So that's pulling the dice downward. Now, what other forces are acting on the dice here? Well, the dice isn't resting against a surface, so there is no normal force here. The only other agent at play here is the string. So the string is applying tension up into the right here. Okay? So those are the only two forces that are acting on this dice. And our direction of acceleration is towards the center of the circle. So our direction of acceleration here is to the right. Okay? So, let's go ahead and draw our free body diagram. Again, it's best when doing these problems to pick your y-axis going up, and your x-axis points towards the center of the circular path. And so drawing these forces on this diagram, we have gravity that pulls down, mg, and tension pulling up and right. Okay? Now, where does this angle theta come into the free body diagram? Well, if this angle here is theta, then if we draw a line straight up here, okay, then this angle here is theta as well. Okay? So therefore, this angle right here is theta. Okay? So there's the setup. And again, if we're doing our centripetal force problem, the x forces have to add up to supply the centripetal force. Okay? And then our y forces, which equal mass times y acceleration, equals 0. Okay? The acceleration is purely in the x direction here. There is no y acceleration. Okay? And that x acceleration, again, was v squared over r. So let's apply these equations, these forms of Newton's second law, to our free body diagram. So let's first look at the x components. First of all, gravity is along the y-axis, so it has 0 x component. So we need the x component of tension. And that's going to be this part right here. Okay? Or that it's equal to this length up here. And we can see that length is opposite the angle theta. So that component is t sine theta. And that has to equal mv squared over r. Now for the y components, we want to find y components of each of these vectors. Let's start with tension. The y component is this right here. It's the adjacent side to that angle theta. So we use the cosine there. Okay. The y component of gravity is mg, but it's negative mg because it's downward. So t cosine theta minus mg equals 0. Okay. So from this first expression, we see that we can solve for the tension, because these are two equations with two unknowns. Theta is an unknown. That's what we're trying to find. But tension is an unknown as well. But we're not interested in the tension. We're only interested in theta. So let's solve this equation for tension and plug it in here. So solving for tension here, we get tension equals mg over cosine theta. Okay? And we plug that in over here, and we get mg sine theta over cosine theta. Okay, so mg cosine theta came in over here, equals mv squared over r. Okay, the masses cancel. This sine theta over cosine theta is tangent theta. Okay, so that's tangent theta. Divide both sides by g, and we get that the tangent of theta is v squared over rg. Or theta, okay, running out of space down here, equals the arctangent of v squared over rg. Okay? So plugging in for velocity, velocity is 25 squared, r is 500 meters, g is 9.8. Take the arctangent of that whole thing, and that gives you an answer. And the answer you get is 7.3 degrees. Okay? So the dice swings out a little bit, 7 degrees, but not too much, just a very slight swing outward. If you take this curve faster, or you go on a tighter curve, that dice is going to swing out even farther.